So for FRQ number 4, we're going to be looking at this graph of the potential energy, of a spring. So part A, it asks us to find the equilibrium length of the spring. So if x is a distance from equilibrium, then at equilibrium, x will equal 0 centimeters. And we can use this constraint by using the potential energy of the spring formula. PE spring is equal to 1/2 kx squared. If you plug 0 into x here, then PE spring will equal 0 at equilibrium. So on the graph, we see that PE spring equals 0 at 20 centimeters. So we can conclude that equilibrium occurs at x equals 20 centimeters because PE is 0 at 20 centimeters. So that is part A, and moving on to part B, it tells us to replicate the graph. So I'm going to draw that right now. And the vertical axis is energy in joules. I spelled that wrong. And then the horizontal axis is distance from equilibrium, or distance in centimeters. So write out the numbers that they have on the graph. So this is 12, 16, 20, 24, and 28. And we're going to draw the PE graph that was given. It's about this. And then it asks us, that's PE. And then it asks us to find, to draw on that same graph a line that indicates total energy. And we know that the turning points are at 14 centimeters and 26 centimeters. And the turning point occurs at the turning point, kinetic energy will be 0 because velocity is changing directions. So if total energy minus kinetic energy equals potential energy, and kinetic energy is 0 at turning points, then total energy will equal potential energy at turning points. So at 14, total energy will equal PE, and again at 26, total energy will equal PE. So we can draw the line for total energy to be about here. And that is part B. And then for part C, it says on the same graph to draw a line for kinetic energy. So we already established that at the turning points, kinetic energy is 0. So we'll write 0 here. And the maximum of the kinetic energy will be total energy, because if kinetic energy max occurs when potential energy is 0. So if potential energy is 0, then kinetic energy will equal total energy. So that is a line for kinetic energy. And then moving on to part D, it asks us to calculate the spring constant. And to do that, we're going to use, again, the equation for PE spring equals 1/2 kx squared. And remember, we said x is the distance from equilibrium. So using the information that we know that at 14 centimeters, total potential energy equals total energy, and we can estimate that to be about 6.5 joules, which is the PE spring at 14 centimeters. So that will be equal to 1/2 k. The change in x, or the distance that the spring is from equilibrium when it's at 14 centimeters, is going to be 20 centimeters minus 14 centimeters. And we're going to want to convert that into meters, into standard unit, because joules is a standard unit. So 20 minus 14 is 6 centimeters. Divide that by 100 to get 0.06 meters. So 6.5 is equal to 1/2 k 0.06 squared. And we want to isolate k because it's the spring constant. So we multiply both sides by 2, divide both sides by 0.06 squared, plug that into a calculator, and we'll get that K equals 3,611.111 Newton times meters, which is the unit for a spring constant. So that's part D. And then for part E, it asks us to determine the block's maximum kinetic energy. And again, we already determined that with the graph, but I'll write it again in using the energy. So total energy minus potential energy will equal kinetic energy. And if KE max occurs when potential energy equals 0. So total energy is 6.5, and we said that potential energy is 0, then kinetic energy will equal 6.5, and that is KE max. And again, we can see that we already basically concluded that on our graph here when we were graphing KE max is equal to total energy, which is 6.5. And then for part F, it says, what is the block's kinetic energy at x equals 16 meters? So we're going to use this formula again here, when total energy minus potential energy equals kinetic energy. And we're gonna convert 16 centimeters into meters so that it will be a standard unit. So that will be 0.16 meters. So breaking that down, we have total energy. Breaking PE down is going to be 1/2 kx squared equals KE at 0.16 meters. So total energy is 6.5 minus 1/2. Spring constant we found earlier to be 3,611.111 times the distance that x is from equilibrium will be equilibrium is at 20 minus 16 centimeters is going to be 4, or equal to kinetic energy at 0.16 meters. And this here is in centimeters, so we're going to want to convert that to meters also, so that it will be 4 centimeters divided by 100 is equal to 0.04 meters. So we'll plug that information back in. 6.5 minus 1/2 3,611.111 times 0.04 meters squared is equal to the kinetic energy at 0.16 meters or 16 centimeters. So plugging that into a calculator, we'll get that 6.5 minus 0.5 times 3 times 0.004 squared is equal to 3.611. So that is joule. 3.6 times 1 joules is the kinetic energy of the spring at a distance of 0.16 meters or 16 centimeters. And then for part G, it asks us, what will the turning points be if the block's total energy is doubled? So again, using this equation up here of total energy minus potential energy equals kinetic energy, we'll define what the energies are. So if total energy is doubled, and we found it earlier to be 6.5, 6.5 times 2 is going to equal 13. So 13 minus 1/2 kx squared, which is potential energy, will equal, so we know that at the turning points kinetic energy is 0 because velocity changes direction, so that will be 0 on this side. and then again we'll plug in what we know here to solve for the distance, because that will tell us where the turning points are. So 13 is equal, move this to the other side, set equal. Okay, so divide both sides by 1/2 spring constant, and we know the spring constant is 3,611 times, or 3,611.11 is equal to x squared, and 13 divided by that is, and then square it, x will equal 0.085 meters. So that is the distance from equilibrium where the turning points will be when total energy is now 13. So if we want to find the actual turning points, then we have to add and subtract this distance x from 20, which is 0.2 meters, which is where equilibrium is, which is converted from 20 centimeters. So 0.2 meters plus 0.085 and 0.2 minus 0.085 is equal to, so there will be a turning point at 0.285 meters and at 0.11.5 meters. If we want to convert that back into centimeters, then we'll have 0.285 meters is equal to 28.5 centimeters, and 0.115 meters is equal to 11.5 centimeters. So those are the new turning points if total energy is given to be double at 13 joules.